Hey, this is Mr. James, and welcome to Vocabulary and Features of Functions and Graphs, Part 2. In this one, we're going to talk about the different parts of graphs that we can talk about. Some of these are going to be new to you, some of them will kind of be review, but we'll go over all of them just the same. And we're going to label some of these graphs on the back side of your sheet, so it's important that you've got probably around 6 colors with you to label these things. Let's start with the intercepts, and I'm going to use red for this. So intercepts. First up, we've got our X-Intercept. Now, you probably remember the X-Intercept is where a function intersects the x-axis, just like this. But what you might not remember is what the actual algebraic definition of the X-Intercept is. And the X-Intercept is where y, or f of x, equals 0. If you look at the y-axis, right here going up and down, at the spots where we intersect the x-axis, y isn't positive 2, it's not negative 5, it's 0. It's the 0 spot right here. So it's actually where y, or f of x, equals 0. The y-intercept, on the other hand, you might know as the place where our function intersects the y-axis, and that's right. But the algebraic definition is that this is where x equals 0, or input is 0. So if you think about the x-axis, the spot where it hits the y-axis is where x equals, boom, right here is 0, where x is 0. On the back side of the sheet, you've got 6 graphs: a of x, b of x, c of x, d of x, e of x, and f of x. What I'd like you to do is go through these and just label where the x-intercepts and y-intercepts are, again in your red color, and please label them whether they're an x-intercept or y-intercept, and also what the coordinate of that point is. So in this case, it's going to be, negative 2, 0. Again, we can see that, look, our x-intercept is where y is 0, since this is 0. Alright, pause the video now and go ahead and fill those in for the rest of those graphs. The answers will be coming up in 3, 2, make sure you've paused. Here they are. Here's A and B. Here's C and D. And here's E and F. Feel free to pause so you can see these a little better. A couple things of note, though, is that look at this. C of X actually doesn't have an x-intercept. Looks like this graph is almost approaching the x-axis, but never actually crosses it. That's interesting. And sometimes, like with b of x, we'll have the graph go through the origin, 0, 0, and so that's both the x and the y-intercept at the same time. Next up, we've got increasing and decreasing. Now, there's a mathematical definition for increasing and decreasing, but we're going to leave that alone for now because it's a little bit technical, and you'll see it in later math classes such as pre-calculus or calculus. For now, let's just know that increasing is when a function is going kind of up from left to right, or the values are getting greater in number. And decreasing is where your values are getting smaller from left to right, getting less. What I'd like to do is flip to the other page, and on each of these graphs, I'd like you to highlight all of the decreasing sections in one color. I'll use orange for this one. Okay, kind of like this. And all of the increasing sections in another color, and I'll use green for this. Go ahead and finish this up for the other 5 graphs. Pause the video now. The answers will be coming up in 3, 2, 1. Here is A and B of x. Here is C and D of x. And here is E and F of x. A couple interesting things of note. Take a look at C of x. It's always decreasing. There's nowhere where it increases. That's kind of interesting. D of x kind of has this alternating thing going on. But in any case, there's this kind of spot on a lot of these graphs where we switch from increasing to decreasing, such as right here, or right here, we're kind of switching it up. Or even when we look at E of x, right here, where it kind of stops increasing for just a second, but then continues to increase. What are those spots called? Well, we can add some names to those right now. Now, the points we were just talking about are called turning points or extrema. For example, if I have a graph that looks like this, right here, okay, these 2 points right here are called minimums or minima. Minima are the least value, the smallest value in this function. Now, a local minima is the smallest value within a certain range. In a range. So for example, this right here would be a local minima. The function kind of decreases and then goes back to increasing in this area. But it's not the smallest or the minimum value of this entire function. This one is. The global or absolute minima is the least value over the entire domain. Okay? So this right here would be a global or an absolute minimum because it's the smallest value this function ever hits. Over here we've got a local one because it is a minimum, but it's not as minimum as this global minimum. To note is that minimums always go from decreasing to increasing afterwards. For example, if we look here, our function is going down, decreasing, and then after the minimum, going back up or increasing. Just like we have minima, we can also have maxima. So let me draw a graph right here, okay, to illustrate what these are. And you can probably guess these are very similar to the previous ones. A local or relative maximum is the greatest value in a small range, So this would be a local maximum because it's the greatest value for everything around it. But the global maxima would be the greatest value over the entire domain. So like this value right here would be our global or absolute maxima. And as a quick note, notice that all the maximums go from increasing to decreasing. So our function's going up as it hits that maximum right there, and then decreases, and then increases to hit its maximum, and then decreases again. The last two vocabulary terms we're going to talk about when it comes to turning points are inflection points and vertical asymptotes. So an inflection point is like this. If you have a graph, maybe it's increasing, and then seems to flatten out, but then continues to increase, or by the opposite, decreases, flattens out to basically flatten and then decreases, this point right here is called an inflection point. Now, there's a technical definition for an inflection point, but we're going to skip that for now. Lastly, vertical asymptote. If you have a graph, okay, that seems to suddenly increase basically to infinity at a certain point, it doesn't cross that kind of vertical line, and perhaps it comes back on the right side, but still doesn't cross that line. That line right there is called a vertical asymptote. Just like inflection point, there's a technical definition for what that is, and we'll deal with that later in the year. But for now, just know it's kind of this line where, as a function approaches it, it's heading off either to infinity, or maybe it's coming from negative infinity, just like that. On this side of the paper, go ahead and try and, using that blue color, whatever color you're using, label your maximums, your minimums. Make sure you label whether they're global or local, any vertical asymptotes you see, and any inflection points. As a little head start, this one right here is actually, it looks like a global maximum, but actually it's not because this function keeps going up even more. So this is going to be a local max, and its coordinates are, it's looking like 1, 2, 3, 4, 4.5, we'll estimate. All right, go ahead and try and label the maximums, minimums, and other extrema for the rest of these functions. The answers will be coming up in 3, 2, make sure you've paused. Here they are. And here's a of x and b of x. Here is c of x and d of x. And here's e of x and f of x. A couple interesting things. In e of x, there is actually no global maximum or minimum, since the function continues to go positive as we go off to the left, and infinitely negative as we go off to the right. There is no exact point we can name on here that is a global max or minimum. Instead, these points will simply be local maximums and minimums. Notice we've got an inflection point here in e of x as well at 0, 0. We've got some vertical asymptotes in f of x where x equals -2. That's kind of the line that would be at that asymptote, and the same thing at x equals 2. Interestingly, in c of x, there's no maximums or minimums to speak of, just this vertical asymptote right here. And d of x has a whole bunch of global maximums and global minimums because it seems like the function continues to repeat. It never passes this point where y equals 1, or down here where y equals -1. So it continues to hit that maximum as it continues to make that wave. That's kind of cool. Now let's talk about end behavior. End behavior is basically how we describe what happens to a graph when we go very, very far to the right, infinitely far to the right, or very, very far to the left of a graph, infinitely far to the left. What happens to that line? Does it go up? Does it go down? Does it kind of tend towards the number? What happens to it? And end behavior is how we do it. So let me draw an example. Let's say the graph looks like this right here. Here's my graph. And let's say as x is an arrow, goes to infinity. What does that mean? As x goes to infinity, well, as you're going towards infinity on the x-axis. So this is as x goes to infinity. What's happening to the graph? Is it going up? Is it going down? What's happening? If f of x, that's kind of this axis, is going to infinity, that means my graph is going up and is continuing to increase towards infinity. On the other hand, if I have this, as x goes to infinity, so x is going towards infinity to the right, okay, if f of x is going to -infinity, that means my graph is decreasing like this as I keep going. So it's going down, down, down towards -infinity on the f of x, or the y-axis. Over here, we can talk about as x goes to infinity, but we can also talk about as x goes to -infinity. And instead of going to the right, -infinity is over here. So as x goes to -infinity, that's going this way, what happens to f of x? Well, if f of x goes to infinity, like we have in this example, it's increasing, it's going up like that. Versus over here, is as x goes to -infinity, so we're going off to the right-hand side, the left-hand side, is f of x going to -infinity, that means we're going down this way like that. Sometimes we have what we call a horizontal asymptote. That's where end behavior doesn't go up or down, it just kind of settles in to one number and starts to go in a straight line almost. So here's an example. Let's say I'm talking about as x goes to infinity, right? But my graph is a little different. My graph looks like this. It's going down. It doesn't go positive, doesn't go negative. It starts to flatten out, and it looks like it's flattening out at this kind of line here where y equals 1. I would say that as x goes to infinity, we're not going to positive infinity, we're not going up, we're not going to negative infinity, we're not going down. Instead, f of x is going to tend to go towards 1 as we go off in that direction towards infinity. So again, end behavior is a way to describe as x is going to infinity or negative infinity, so to the left or the right, what's happening to the graph? Is it going up towards infinity? Is it going down towards negative? Oops. Is it going down towards negative infinity? Or is it kind of settling in to one number and kind of going flat line, and that's called the horizontal asymptote. Using that same color, let's go ahead and try and label some end behavior on these graphs. I'll do the first one to show you what I mean. So on this side, we have x is going to infinity, because this is going to the right. What's f of x doing? Well, it's going down. So I'd say f of x is going to -infinity. What about the other end of my graph? Well, on this side, this is where the x values are going towards -infinity. So as x goes towards -infinity, what's happening to the graph? Well, it's going up. F of x, this direction, is going towards positive infinity. Get out a positive sign if you want, and there it is. Go ahead and try and fill in the end behavior for the rest of these graphs in that same color. The answers will be up on the screen in 3, 2, 1. And here's a of x and b of x. Here is c of x and d of x. And here's e of x and f of x. A couple interesting things to note. In f of x, kind of like we talked about before, there's a horizontal asymptote. So as we go off as x goes to infinity, going off in this direction, f of x doesn't go to positive infinity, doesn't go to negative infinity. No, it doesn't do those things. Instead, it kind of settles in and just goes towards 1. Right? It gets closer to 1. Same thing as we go towards negative infinity, it gets closer to 1. And c of x is the same kind of thing. But d of x, what's going on there? It keeps going up and down, it's oscillating. I don't know where it's going in its end behavior. For this, we can use the word periodic or periodicity, which means repeating values within a certain interval. And there's a couple examples here. So although we really can't talk about the end behavior, I would call d of x a periodic function because, as I'm showing you, the values continue to repeat over and over.